Okay, so as I told you, the starting point of the first exercise was the bandpass filter that we designed yesterday that was not that good. Okay, and the goal of the first exercise was to get a better bandpass filter. So I start by loading the data. Okay, now some of you got already a bit in trouble with the load command. Okay, this is how you load a MATLAB data file. Okay, and it brings the variables into the memory. Okay, no need to do anything more complex than that. Yeah, and so where are you? Here. Okay, so here's the plot, and I like to have the plot docked on the in the MATLAB window itself. It doesn't disappear every time I try to write code. Okay, but that's up to you to decide how to do that. Okay, so let's see what I said. Plot a few tiles, try to find by hand the right upper corner frequency. So the point, again, the problem yesterday was that the spikes got hit. The upper corner, 2 kilohertz that we used for the bandpass filter was too low. So in order to figure out what a good corner frequency could be, I have to look at the spikes and verify that I use the corner frequency high enough not to distort them. Now, the typical frequency that would compose the spikes can be estimated from its width. Okay, and its width, you can see it from here. It's about order of 10 samples. And since the sampling frequency is the sampling frequency is 24 kilohertz, 10 samples is about 1/3 of, again, order of magnitude, about 1/3 of a millisecond. 1/3 of a millisecond is 3 kilohertz. Okay? Now, these transformations, again, are things you should be used to make. Okay? It's useful and it will give you a very fast sense of what's going on. Okay, so we want to be at 3 kilohertz or above. So let's start with 4 kilohertz. So I want to design now, okay, so that's my estimate by hand. Okay, so I want now to have a high-pass filter with that, a bandpass filter with that corner frequency. So I go back here. That's the bandpass filter. Okay, I reuse the text that I already have. And here I write the 4 kilohertz instead of the 2 kilohertz. So in principle, the whole purpose of this part of the exercise was to change the 2 kilohertz into another number. Okay, I thought it will be easy. Okay, you'll find the line and just change the number. Okay, there's nothing shouldn't have been very difficult. So here's the flex Z, corner frequency shifted to a 4 kilohertz. Okay, and here's the plot. happened? Yeah, T. Okay, and this spike, for example, is a line that it's a shoulder, so I'll magnify it in order to look, to make sure. So that's already better. It's still, you can still see that the smoothed version, it's a bit wider than the original one. Okay, it's not 100%, but that's already better. At least it's not decreasing in size. Okay, so next, I asked to test a few values for the lower corner frequencies. Okay, so I'm going to design the filter, and now I'm going to change this here, for example, to 50. Now I have to be careful here. What should I change in addition to the 50? Yeah. So 240 was the period of a sine wave with a frequency of 100 Hertz. Okay, and now my lowest frequency of interest is half that. Okay, so the filter should be longer. You know what? I'll design it that way, and you will see. We'll run the Freq Z, and we'll see what the problem is what's going to happen. Okay, so if there is a problem, it's going to be here at the lower edge. Okay, so remember my corner frequency, the corner frequency that I asked was 50. Okay, and I would like eventually, the attenuation to go down. Let's go back. The attenuation should go down to large values, okay, below minus 60 and so on. Okay, now if the window is too short, okay, then you can see here the attenuation never reaches very low values. It goes down to about minus 30 dB, but it can't go down below that. Okay, and the reason that it can't is because the window is too short in order to get rid of these very low frequencies. Okay, the window that you use has to be long enough so that it captures the low frequencies that you want to remove. Okay, so instead of, let's do it, make an extreme case. Okay, I'll design a filter with a window that's far too short. Okay, so you can see it cannot attenuate these low frequencies. Okay, that's okay. So let's get back. So it should be like that. Now, if this is my low frequency corner, okay, and now the attenuation goes down indeed to at the lowest frequencies, it goes down to below minus 50. Okay, so that's the effect of the length of the filter. Okay, now I can filter. Okay, so what is good and what is not good? I got rid of the very slow, very large fluctuations, but note that here, for example, I have these things, pretty large things going up that's slow. Okay. Now, also the spikes are not flattened, if you wish. They ride on something. Okay, you see them riding on and so on and so forth. So the difference between 50 Hertz and 100 Hertz in terms of removing frequencies are precisely these type of fluctuations. Okay, these fluctuations were removed when the corner frequency was 100 and are not removed when the corner frequency is 50. Okay, and again, you can see this. Here, the period of that thing, I go from about 0.05 to 0.07. Okay, so this is 20 milliseconds. 20 milliseconds is 50 Hertz. Okay, so it's exactly this range of frequencies between 50 and 100. Okay, that now appear in the signal because I didn't remove them. Okay, but they are much lower than the spikes, and they cause the spikes to lose this constant baseline. Okay, let's see what happens if I'm going to a much higher corner frequency. So now I have two possibilities. So I'll go to 500 Hertz. Now I have two frequencies. I can leave this number as is. Okay, the filter should be at least as long as. So the fact that it's much longer doesn't make it not work. Okay, it's wasteful. So if I want, I can also reduce the length of the filter, but it doesn't matter much. Okay, what it affects is these transition bands that we discussed yesterday. They become narrower the longer the filter is. I don't like long filters, so I'll make it shorter. Okay, so this is the filter. Again, the low corner frequencies move to 500 Hertz. Okay, what happened to the spikes? What happened to the spikes? Well, they got distorted. Okay, they got distorted because I start to hit them now from the low frequency side. Okay, they contain frequencies. If you remember again from yesterday, when you look at the power spectrum, they contain frequency at around 400 Hertz. Okay, which this filter removed. So their shape is now distorted. Okay. Okay, next. Calculate the power spectrum with a DPSS. So again, the code is in the code is here. So I'm looking for it. Power spectrum. And here's the window. Here's the DPSS. Okay, so I copy. So that's a calculation of the DPSS window. It's a kind of look a little bit like a Gaussian. Okay, this is the code for calculating the power spectrum. So first of all, here I multiplied each column of data by the window. Okay, so again, look at the MATLAB help in order to figure out what happens here. RepMat takes this column, replicate it once in the column direction, and replicate it 500 times in the column direction. Okay, and then I'll multiply this by data. So I multiply each column of data by the window. And then I do an FFT, okay, and then I take abs squared and calculate the mean over the columns. This is this 2, okay, and then I cut everything by 2. And right now I don't have a frequency axis to plot it, so I will generate a frequency axis as well. So F equal 0 to So here's the power spectrum. Now, for the 200 Hertz, we looked at it yesterday. Okay, so this peak at low frequencies is caused by the local field potentials. And you can see here why 100, 200 is a good number to stop. That's about the valley above which you start to get frequency contribution from other stuff. And we had identified this thing around 400 Hertz as part of the spikes. Okay, that's from yesterday. So 200 Hertz is a good corner frequency here. Now, yes.
Wouldn't you like to cut the other one to the right of that 200?
Which?
Around 350 or something?
What, this narrow peak? Yeah, I may want to cut it.
And since we saw that if you name it 300, so it's not really 300, but it's...
Yeah, but I don't want to hit the 400. Okay, I don't want to hit that peak. And with the filter that I have, separating between this peak, this thing presumably comes from the 50 Hertz interference, the harmonic of the 50 Hertz interference. Okay, but it would be very difficult to put something that would suppress this very much and wouldn't hit that. Okay, so I'd rather live with this, okay, and not distort the spikes. Okay, that's... So the question is how far to go. So I follow these peaks of 400 Hertz, 800 Hertz, 1 point something, 1.6 something, okay, around 2 kilohertz. And then maybe this belongs to that sequence too. Okay, and then I start to have this noisy stuff. So I can make a decision, okay? I can say that I want all of that, I will live with that junky stuff, and I will put my corner at 4 kilohertz. Okay, like we determined, like with the hand-waving approach. Or I can say that the contribution of this is going anyway to be masked by the noise that comes from this noisy stuff, and I'll put my corner frequency at 3 kilohertz. And as I said many times, this should not affect the results. Okay, so try this, try that, look, do whatever you want to do with the spikes after that. And if it does matter, you probably made a mistake somewhere else. Okay, that's, so the end decision is that it should be like 3-4 kilohertz here. Okay, and my point, again, the point of the exercise is that I reach the same conclusion looking at it in the time domain and looking at it in the power spectrum. The difference was that in the time domain, I had to understand maybe better the signal. I had to zoom in on the appropriate fast events and use them to calculate the corner frequency, whereas in the power spectrum, the whole information was given to me at once, and if I know how to read the power spectrum, I don't have to look for the interesting events by hand. Okay? On the other hand, unless you know how to look for the small things, the interesting events by hand, you'll probably not understand the power spectrum. Okay? So either way, you need to be able to figure out both. Another thing that I wanted you to notice the way that I did it. Okay, I almost didn't write a single additional code. Okay, everything was cut and paste from the scripts, and this is how it will continue to be. Okay, these exercises are not about writing MATLAB code; they are about using the tools that I taught you, and the tools are in the files. Okay, so that's. Okay, question number 2. Oh, why would it be easier to process the spikes after filtering? For example, yeah, if you want to threshold them, then let's even, I'll plot the bad one here. No, I want to plot that one. If you want now to detect the spikes, okay, the way that you detect them, spikes are large negative events. Okay, so you want to set a threshold, but if you didn't high pass correctly, in this case you didn't high pass enough, okay, the baseline out of which the spikes are going to start is shifting. Okay, and so in order to detect that one, you need a relatively permissive threshold, but if you will put a threshold here, you will also detect this junky stuff. Okay, so you want to, in order to threshold well, you want all the spikes to start from about the same baseline, which means getting rid of slow fluctuations. So that's why you need to high pass. Okay, good bandpass filter for vfigure.mat. Okay, let's clear. So I want to, again, to recalculate the power spectra for the up and down states. Here's the code. That's the part where I extract the up and down states, and here I calculate the power spectra, and here I plot it. Oh, this is what I wanted. Okay, so I extract the up and down states. This is after I subtracted the mean. I mean, that's a plot that we had on Monday, 2 days ago. So here I calculate the power spectra. The length of the segments over which I calculate the FFT is 20,000. That's 1 second worth of data. So this will give me the power spectrum with a resolution of 1 Hertz. Okay, and I call P Welsh with arguments. When you call P Welsh with arguments, it doesn't plot itself. Okay, it provides back the data. So this is the power spectrum, and these are the frequencies at which the power spectrum was calculated. Okay, that's for the down state. This is for the up state. I could get the F also for the up state, but it would be exactly the same as for the down state, because all the parameters are the same. These are the same and these are the same. Okay, so the list of frequencies at which it is calculated are the same. So I have now a frequency axis and the power spectra. Okay, now I have them. Okay, and now I plot. So this is something that, to that point, I guess that was one of the last things that I showed you on yesterday. And we see from here this range of frequencies over which at which the up state has more energy than the down state. Okay, that's the. Okay, so this we did in the lesson. Now, calculating the power spectra with different frequency resolutions. So I didn't say it explicitly in the lesson, but I'm saying it now. This means changing this parameter, and actually I did say it. Okay, it's on the slide from the lesson that describes P Welsh. Okay, the slide that explains the parameters. Okay, so let's just copy this again. Okay, no need to. And I just want to change this. Okay, so let's do a dramatic stuff. Instead of I'm using now frequency resolution of 10 Hertz instead of 1 Hertz. What happens to the power spectra? Okay. They became smoother, yeah? This is what reducing so if you reduce this number, okay, if you calculate at less frequencies, you effectively increase the width over which you average the energy, and that makes the estimates less noisy. How far should I go doing this? Okay, at some point, my frequency resolution will start to hit the interesting features. Okay, so I may be interested in something that's narrow in frequency. For example, I may have a pure tone in the data. Okay, if I reduce the frequency resolution, then the pure tone will widen. Okay, we will see it in 2 weeks' time. Okay, but here it doesn't matter much because I'm interested in features that are pretty wide. Okay, so I can reduce the frequency resolution even further. Okay, so now I'm using frequency resolution of 100 Hertz. Okay, even smoother, still, you can see how you lost the information. I mean, these things were a lot of, okay, in the original version, okay, these things here have a lot of narrow lines. Okay, and if I reduce the frequency resolution, I don't see the narrow line, all I see are the peaks. Okay? But the part that interests me is here, so that's fine. Okay, I can still see this frequency range at which the up and down states are very different from each other. And I can go even further. The point again in doing these gains is that you can see, you should be aware at how easy it is. Okay, MATLAB is calculating now a large number of short FFTs, but it takes time. Okay, eventually it will plot something, it will be funny, but okay. So now I lost the information that interests me. Okay. Why? It goes over about 1 kilohertz. The resolution here is 1 kilohertz. Okay, so I lost the information. So that was a better way of looking at it. Okay, next. Design a bandpass filter that would emphasize the right frequency range. So the right frequency range is here. So it starts here at about, I don't know, let's put a grid. Let's say 150 Hertz. And it goes all the way to let's say 2 kilohertz, or 2.5 kilohertz, 2 kilohertz. What was the low frequency I said? What? 150. So 150 to 2000. Okay, 200 to 2000. So B equals phi 1. The lowest frequency that I have is 200, which corresponds to a period of how many data points? Sampling frequency is 20 kilohertz, so that's 100 points. Okay, so the duration of the filter should be 300 points. Okay, the frequencies are 200 and 2000. Okay, that's it. So this is the impulse response of the bandpass filter. Okay, the fast fluctuations have to do with the 2000 Hertz corner, and this slow shape, okay, that goes like that. Okay, this has to do with the corner frequency at 200 Hertz. Okay, it has the right corner frequencies and so on and so forth. Okay, so now I filter. So I part 1 will be field. And I part 2 will be field. I don't remember, did I subtract the means or not? Yeah, I subtracted the means. Okay, so red is the up state. So you can see, I mean, once I did that, the difference between the up state and down state actually looks even more dramatic than when I did it by hand on Monday. Okay, that's it's not surprising. Okay, I did it using better tools and more precisely. Okay, I can calculate again the variances. Okay, and okay, so the variance ratio comes out to be 5.6. If you remember, it was 4 point something yesterday. After I downsampled, it came to 5.4. Here I didn't downsample yet. So if I want to repeat the whole process that we did on Monday, I should calculate now the cost correlations. Okay, so I could go back to the script from Monday. I'll just type that. Idiot. That was supposed to be plot. So, I mean, the good news is that once I used the right filter, I got rid of the low frequencies much better. So the correlations go to zero substantially faster. I still had to downsample, but not by a factor of 2000 like I did on Monday. Okay, it's enough to downsample it by a factor of 100, and I will already get points that are roughly independent. Okay, so this is for the down state and for the up state. Okay, that's okay, so 100 would not be enough, but 200 is good enough. Okay, so I'm going to downsample by a factor of 200 instead of 2000. Now the reason that I can do that again is because I used a better filter. Okay, the filter I used to remove the low fluctuations on Monday was a really bad one. Okay, and again, the important lesson here is I'm doing much better when I'm using these tools. Okay, Fear 1 is much better, designs much better filters than these moving box filters that I used on Monday. The thing is that on Monday we got the results too, okay, although we used very coarse tools. Okay, so I'm going now to extract the relevant point. So okay, so these are the variances that I want to look at. The ratio is 5.57. Okay, so that's very similar to the one that we had on Monday, but the number of degrees of freedom is now substantially larger. Okay, so I have now 501 points instead of 51 points. So the strength of the statistical test is much better. If you remember, already on Monday, we got a significance of 10 to the minus 11 or something like that. So the fact that I get an even greater strength for the statistical test is not really, okay. I didn't gain any practical advantage. Okay, and okay, I'll skip. I can either finish exercise number 2 or do number 3. What do you prefer? 3? Okay. Okay, so I provided the code for generating a sine wave. I don't like variables that start with a capital, except what?
Sampling rate with small n. And another one just after.
Yeah, thanks. So x-axis is in seconds, 0 to 5, and this is supposed to be a sine wave with a frequency of 2 Hertz, so there should be 10 cycles. Okay, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. MATLAB knows trigonometry. Okay, now this is what we call actually cosine phase. Okay, it's 0, it's the maximum, and it goes down. Okay, so this is like a cosine. Okay, not like a sine. So this is a sine wave in a cosine phase. Okay. Frequency, sampling rates, phases. Okay, so let's first of all try another frequency. Give me a frequency. Which frequency do you want to plot? 5. what I expect to see. How many cycles should there be? How many cycles should there be? It's 5 hertz, 5 seconds, 25. I'm not going to count, but I rely on MATLAB. Okay, let's change the sampling frequency. So which variables do I have to change in order to change the sampling frequency? And then, okay, let's take sampling rate of 1000. What else? Okay, my time window, my time scale. Okay, and then we are going to what changed? Essentially nothing, okay, because even at 1000, I have 1000 points in 1 second, okay, and that's a very high resolution. So the fact that I went from 32K points in 1 second to 1000 points in 1 second doesn't affect the quality of the graphics, okay. Let's reduce the sampling rate even further. Okay, 100 hertz. What changed? Still nothing. Okay, if I magnify things, I'll start to see, okay, you start to see here the fact that the sign is not completely smooth. Okay, let's go even to a lower frequency. Which? Give me a frequency. 20. What happened to the sine wave? What happened to the sine wave? How many sample points do you have in each cycle now? 5 hertz, 20 points per second. How many points per cycle? No. 20 points per second and 5 cycles per second. So how many points per cycle? 4. Okay, so let's look for them. So I'm going to plot it. Okay, this is going to plot a dot on each data